Hello everyone, my name is Angelo and my topic for the seminar is auto-cleaning dirty data and more specifically the Data Encoding Bot. Let's first quickly move this up to the top so that it's not intervening with what we want to do. So first of all, let's have a look at the topics that will be covered today. We'll start with a short introduction, then we'll move on to the problem formulation. Let's have a look at the already existing literature. Then we'll describe our proposed solution. We'll have a look at our results. And then we move on to a short conclusion and a short discussion. So let's first do an introduction. Machine learning is getting more and more popular by the day. People use machine learning to discover things that they themselves are unable to do because computers can almost do anything, and machine learning is the new holy grail. So basically, machine learning is used for knowledge discovery, and machine learning uses machine learning algorithms. But these machine learning algorithms need clean data as an input. However, machine learning is getting more and more used by the day, so more and more people are producing data, which leads to massive data production. And when people produce massive data, then human errors are involved simply because people make mistakes. And now the problem is machine learning algorithms need clean data as an input, but humans produce dirty data, raw dirty data. And therefore we want to do data pre-processing or data cleaning, and we want to do it autonomously. So basically the problem is we have a lot of dirty data and we would like to autonomously turn it into clean data. So basically the process of turning dirty data into clean data consists of four data encoding bot, an outlier detection bot, an imputation bot, and a feature selection bot. However, for the scope of this project, we'll only focus on one aspect, which is the data encoding bot. Let's have a look at what the data encoding bot basically does. The data encoding bot consists of three different steps. The first step is auto-detecting data types per feature, per column. Note that feature and column are used as the same term in this presentation. The second step is auto-detecting numeric, categorical, and ordinal features. And the last step is auto-selecting encoding techniques for all features based on the output of the first two steps. So the problem for the first step is we'd like to auto-detect data types such as strings, floats, integers, bools, and dates. And this is very easy to differentiate for human beings, but it's already relatively hard for computers and automated processes. Then the next step is we would like to auto-detect ordinal and categorical features. We have numeric values, which are just real values or measurements, categorical values which can be put in a category, and ordinal values which also have an order in them. And this is still quite easy to differentiate for human beings, although ordinal is already getting more and more difficult for people as well. But this is very hard for computers and automated processes, and this is the major problem of this data encoding bot. The third step is auto-selecting encoding techniques. We would like to find an optimal representation for the raw data that's the input based on different algorithms. So machine learning uses a lot of different algorithms such as tree structures, SVMs, nearest neighbor, and all of these different algorithms take very different encodings as optimal input. And the problem is that non-optimal input can lead to incorrect predictions. Let's have a look at the solutions that already exist out there. So what's the state of the art? For the first step, we have two solutions, brute force guessing and Python pandas. Brute force guessing basically is the fact that for every value in a feature, you try to convert it into every possible data type, and you count the number of successful conversions for each data type, and then you multiply this number with a weight specific for each data type, and the highest number basically wins. The other solution is Python pandas, which is already out there, So a lot of people use Python and use pandas, and pandas has the read CSV function that already automatically infers data types from a CSV file. But it only does this for integers, floats, and considers the rest to be strings. For the second step, auto-detecting categorical and ordinal features, there's also a number of approaches. There's a simple approach which detects only categorical features. That's the major downside of this approach. But it's very simple. It uses only two rules. You check for a feature whether it contains either only integers or either only strings. And when it does, you check for the number of unique values. If the number of unique values is smaller than or equal to a predefined or user-defined number of n, then it's considered to be categorical. There's another more sophisticated method, which is the Bayesian method. It detects both count, so numeric values, versus categorical data versus ordinal data. And it has a more statistical approach where it uses a likelihood function for each of these data types to determine how likely it is that a feature has that particular data type. The third step of the process is there's not a lot of information and research out there because we have a lot of different machine learning algorithms. It's not really clear what is an optimal coding for these machine learning algorithms. And basically, it is the problem of deciding whether you should one-hot encode a feature or not. One-hot encoding is putting every unique value of a feature into its own feature and indicating with ones and zeros whether it occurs or not. And there's also another solution which was proposed by someone on the internet, which is binary encoding. Binary encoding basically is turning all unique values from a feature into a long binary string. And for each digit in the binary string, you create a feature, which creates less features than one-hot encoding, but has some distortion of information. Let's have a look at our own proposed solution. So we have the first step of auto-detecting data types. We go back to the data types that were proposed earlier. So how do we infer these types? And what we do is, first of all, we use the read CSV function from the Python pandas functionality. So the input is a CSV file, and the function reads the CSV file and ultimately infers integers, floats, and decides that the rest of the data types is string. So we'll see later how it actually, what the results are, if it works correctly or not. But one of the problems that isn't working that well is that when there are missing values or there are incorrect values, then Python just infers it, or pandas just infers it as a string instead of an integer and float. So for all the string or object features, we have to check whether it's a integer, string, float, bool, or date. So checking for booleans is easy. It's just checking for a number of unique values, and if this number is equal to 2, it's boolean. And we also do this for the already inferred integer columns by the Python pandas library, because integer features can be boolean as well. Then we want to check dates. Dates are quite easy to check as well. We just check for the number of symbols that it consists of, and if this number is equal to 10, and if there's a dash or slash at positions 3 and 6, or at positions 5 and 8, then it's a date representing the different notations there are. Then we have integers and floats, which just convert a value to an integer, and if it works, then we know it's a number. If this number, the original value, contains a point, then it's a float, and otherwise it's an integer. And if it's none of the aforementioned data types, then everything else is a string. So now we know which data types there are. We'd like to auto-detect categorical features. We have two different categorical features. We have categorical strings and categorical integers. Let's start with categorical strings. We use an approach that is based on human nature. First of all, we check for the number of different unique values. If it's smaller than 25, we automatically infer it as categorical because it means that the number of unique input values is that most of the times it's categorical. And if it's bigger than 25, it's smaller than a predefined user-defined value k, then we try to calculate a similarity score based on the Wu-Palmer algorithm. The Wu-Palmer algorithm uses the function that's stated on the slides, where the notation synset basically just means looking up a word in a dictionary in a corpus, and then you try to find, for example, the similarity between vehicle and fork, and then the depth of synset 1 is the depth of vehicle, which is 5, the depth of synset 2, which is the depth of fork, is 7. Together this is 12, and the LCS means basically the most common thing that combines the two. So the first grandfather that has both of them as their grandchild, which is in this case artifact, which has a depth of 2. So 2 times 2 is 4, divided by 12 is 1 over 3. So the similarity score between the vehicle and the fork is 0.33 or 1 over 3, which indicates they're not really related, which is quite obvious. So we calculate a score for every unique value in our feature with every other unique value in our feature, and then we get a mean similarity score, and this mean similarity score should be larger than 0.5 to indicate that they have at least something in common. Then we also want to know if we have categorical ints. Basically we do the same thing, but now first of all we check if the number of unique values is smaller than 10. If it is, it's categorical. If it's not and it's bigger than 10 or smaller than the user-defined value k, then we calculate a distance score between the integers, which is basically just the absolute difference between two numbers. And we do this for every unique value with every other unique value again. And then the mean distance should be smaller than the mean of the feature. So for example, if we have a column containing the numbers 1, 5, 16, and 3, then the distance scores are the difference between 1 and 5 is 4, 1 and 16 is 15, 1 and 3 is 2, etc. Then we have a total distance of 47, which gives us a mean distance of 7.83. And the mean of the feature is 6.25, so this feature is not categorical. Then the last step is auto-selecting encoding techniques. So now that we've decided which features are categorical, we'd like to one-hot encode them. And we do this one-hot encoding based on user-specified parameters, which are the number of occurrences. The number of occurrences basically states how many times a value should occur before it's one-hot encoded in the feature. And we have a parameter other, which indicates whether the unique values that are not included in one-hot encoding because their occurrence is smaller than the number of occurrences should get a feature other, where all these unique values, the remaining unique values, are combined into one feature such that we have no loss of data. Then we have our non-categorical features as well, and we would like to factorize them. Factorizing is assigning a unique integer to every unique value in a feature, and we'd like to do this such that we get an all-numeric representation of our raw dirty data. Another solution is that that the non-categorical features remain untouched, such that, for example, date features remain in their origin, as they might be the indicating value to combine this raw data with another data set which also contains dates. And then we have the integer and float features, and they remain untouched because they are already numbers. Results for step 1. Well, we've used 10 different data sets. And why only 10? Because it's very hard and very time consuming to determine the ground truth for each data set. which has to be done manually. And that's why we've only used 10 data sets. For each of these 10 data sets, we calculate an accuracy score, which is based on the number of correct predictions divided by the number of features checked. And as can be seen, for step 1, we have an average score of 100%. For step 2, auto-detecting categorical features, this is a bit different. We can see that the lowest score of 70% is with the one reviews, but we have an average of 90%, which means this step still makes mistakes, which is basically due to the fact that when we'd like to create a similarity score between words, and there are words that are not that cannot be found in the corpus because they are not part of common language, then we cannot calculate a good similarity score, and as such we have different incorrect results. Finally, we have the auto-selecting encoding technique step, and there's no clear way to measure efficiency. It's up to the user to decide what's an optimal encoding. We have several parameters that can be user specified, such that the encoding can fit the aims and needs of the user, such as the other column, the number of wanted encoded features, and whether or not we should factorize remaining features. Conclusion. So it was very easy on the eye, but it was much harder in reality. Step 1, results were above expectation and it was relatively easy to implement. We've used a combination of several existing approaches plus a human approach. Step 2, on the other hand, caused major problems and was the most difficult aspect. First, we tried a machine learning approach, but it didn't work because of it's very hard to get training data based on categorical and ordinal data. It's very time consuming to produce yourself, and it's because you're working with dirty data, it's all quite complicated, and in the end machine learning didn't work. Able to detect ordinal data, and the downside is the difference between categorical and ordinal data is paper thin. Solution is that we implemented a human approach, which is the proposed solution that I mentioned before. Step 3 has a proposed solution, but the problem is there are no clear metrics for this. Discussion, what could have been done better. Step 1, dates. Dates are a major problem because in most computers you have date combined with time. So one value represents a date and a time at the same time, which is very hard to detect for this implementation right now, as well as dates that are represented by one digit. So for example, if you have months January until September, which are 1 to 9, then they need to be represented by 2 digits, so 01 to 09 for our function to discover them as dates. Step 2, we'd like the introduction of machine learning because our machine learning approach didn't work. Further research needs to be done in this direction. And obviously the detection of ordinal data, because we couldn't manage to detect ordinal data, that's one of the biggest points of further research. Another point is determining ground truth, because it's very time consuming to manually determine ground truth, and it's also very subjective because it's basically my own idea of what should be the ground truth. Categorical string detection, as mentioned before, is a problem because there are many user-defined words that are not in a corpus and that lead to an incorrect calculation of a similarity score. And the influence of critical values use needs further attention because we've used critical values for categorical strings, categorical integers, and the similarity score and distance score, and all these critical values have only been investigated minimally and need further research. Then for the last step, we have an optimal encoding based on the raw data and based on the algorithm that's going to be used, because we've added parameters that can be user specified, but we need further investigation to find metrics for an optimal encoding. What is an optimal encoding and how do you define it in measurements? I've included the references to a few pages that are in my presentation and paper. If you're interested, just follow the links. And another page which contains basically all the information that you need. And if you have any questions, just contact me on my TUE email. And I'd like to thank you for listening.